In this tutorial, I'm going to demonstrate how to set up and run an in-situ EELS spectrum imaging experiment in GMS 3.4 using the GIF Continuum and a Wildfire heating holder provided by Den Solutions. The SI data is acquired in multi-pass mode, and each of the individual SI passes is saved separately. By combining concurrent standards, live mapping, and script control of the Wildfire holder, I have designed a method that allows me to perform live oxidation state mapping in situ as the temperature is changed. The microscope I'm using is a Joule F200. I'm running the experiment at 200 kV and using a short camera length, which gives an optimized collection angle for EELS in the spectrometer. I'm using the second lowest energy dispersion of 0.75 eV per channel and the large high SNR aperture, which is a good filter setup for fast mapping in the continuum. Right now, I'm looking at copper-2 oxide and silica microparticles on one of the silicon nitride windows of a DENS Wildfire chip. I already set up the spectrum image parameters. I'll be capturing SI data from this 2D array with drift correction active. I've set the drift correction measurements to run after each SI pass is completed. I'll go ahead and hit capture and talk over some of the key aspects of the experiment as the data is acquired. For this experiment, I want high time resolution, so I've chosen to run the spectrometer in HS Plus mode. HS Plus supports a maximum spectral rate of 8,700 spectra per second with greater than 90% collection efficiency. I'm running in dual EELS mode. The spectral rate shown is for the dual EELS pair, so to get the true data rate we need to multiply by 2. So right now I have 7,400 spectra per second. The duty cycle, or collection efficiency, for the high loss is close to 100% as I've matched the high loss time to the camera frame rate. As the low loss time of around 0.1 microseconds is much shorter, the collection efficiency for the low loss is closer to 0. So what we end up with is a duty cycle for the dual EELS pair, which is approximately halfway between the two, so 48%. I'm using dual EELS so I can use the low loss spectrum for pleural scattering correction. The copper oxide particles that I'm interested in have a really big change in thickness. It's important to be able to correct for this to perform good analysis and mapping. For more detail on pleural scattering correction, watch the model-based EELS quantification and LNES phase mapping webinar on the Gatan website or our YouTube channel. Collecting the low-loss spectrum also allows for post-acquisition energy scale correction, which is also critical for good EELS analysis. That won't be necessary in this case as I'm using ZLP lock. ZLP lock performs live energy scale correction as the continuum data is collected. This correction is applied to both the low loss and high loss data in real time and is particularly useful for multipass spectrum imaging and live mapping. I matched the SI pixel time to the maximum camera frame rate, and I've chosen a pixel size of around 8 nanometers so that the time per SI pass is approximately 1.6 seconds. I'm capturing 150 passes and live mapping is enabled. I'm using a saved analytical setup that uses concurrent standards for copper. This allows me to map different oxidation states as the temperature increases and monitor the redox reaction as it happens in real time. Let's move on to the Wildfire control. The Wildfire holder can be controlled with the GMS plugin, which allows us to set the temperature directly, create certain temperature ramps, or complete recipes for an entire experiment. So this is covered more in a separate tutorial video, again, on the Gatan website or our YouTube channel. The most effective and robust way to synchronize the temperature ramp with spectrum imaging is to use scripting. First of all, we need to customize the spectrum image acquisition process. This can be done with a script, which we call an SI script hook. A script hook essentially tells the software to do something non-standard at some point in the capture process. For a full explanation and some script hook code examples, just look at the scripting section of the Digital Micrograph help, where this is really well documented. Here I'm using a script hook which tells the software to run a second script before each drift correction in the SI acquisition. The second script prompts the Wildfire holder to increase the temperature by 4 degrees C, reads back the temperature, and exits only once the target temperature has been reached. As I'm performing drift correction at the end of each SI pass, this allows me to acquire an entire SI pass at a fixed temperature, pause the acquisition while the temperature increases, perform the spatial drift correction, and then collect another pass at the new temperature and then repeat. This is a very powerful way to automate the experiment. This dataset has 150 passes and goes from 100 to 700 degrees Celsius with a temperature resolution of 4 degrees Celsius. Live mapping allows us to monitor the experiment in real time, but as the passes are stored separately, the important processing decisions such as the optimum spatial, spectral, or temperature binning to use can be made post-acquisition. Being able to make these decisions after the experiment is highly desirable, especially for a one-shot experiment. That's all for this tutorial. Thanks for listening, and I hope you enjoyed the demo.